Check. Hey. Okay. Awesome. 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 Mm-hmm. Great. Okay, thanks for wading through that. We're going to be looking at the last 5 questions. Okay, let's start with question 18, I guess. I just realized I need to check something. Okay, not cool, but okay. All right, so the first one is we're supposed to use a comparison test to state whether this converges or diverges. So we've got pi to infinity of 2 plus cosine x over x squared dx. And this is similar to what we did in class already. So let me just say that since that denominator is x squared, so the denominator is x squared, so it's likely to converge. Basically, the exponent is strictly greater than 1. So that means we would like a larger function. That converges. Okay. So you can't really do a whole lot to the denominator, but you can do something for the numerator. So for the numerator, we want to maximize, make this as big as possible. 2 plus cosine x. So what's the biggest that will ever be?
3.
Okay. That's always going to be less than or equal to 3. So we're going to check the integral from pi to infinity of 3 over x squared dx. Okay. I'm going to do this pretty properly. The limit as the upper limit goes to infinity from pi to b, 3 over x squared dx. Antiderivative of x to the negative 2 power is negative x to the negative 1 power. Got my limit. substitute. Negative 3 over b plus 3 over pi. This here goes to 0. So this limit converges to 3 over pi. All right, so most of our work is done now. We can say that 2 plus cosine x over x squared is always less than or equal to 3 over x squared. And since from pi to infinity of 3 over x squared converges, pi to infinity of 2 plus cosine x over x squared also converges. Which one? Yeah, I got it. The idea here is we want to maximize this function here. And what's the biggest that this can be? Well, 2 is already as big as it can get. The biggest that cosine can ever get is 3.
1.
Is 1. I'm sorry, is 1. So 2 plus 1 is 3. Mm-hmm.
So if that was on the bottom, so you basically want to make cosine negative 1, or the smallest it can be?
Yeah, the smallest that cosine can be is negative 1. So if you're looking to make the same thing diverge, which it won't, but if you're trying to make it diverge, you would use cosine as negative 1 and 1 over x squared. In that case, I think you can probably see that the smaller function is going to converge. So you wouldn't be able to show anything. Okay? Next question. Number 19. You have the integral from 1 to infinity of natural log of x over x dx.
Just do u equals on x.
Oh, you can actually integrate this. But it says to use the comparison test. You bring up a good point. Let's use the comparison test first, though. Using the comparison test, my denominator here is x to the first power. So we think this is going to diverge. Probably diverges. I can't really do anything to the denominator, so I have to figure out something for the numerator. And I want smaller. I want smaller than that, right? Okay, so I need a function that's smaller than natural log of x. So natural log of x, after a certain point, it's always bigger than 1, right? After a certain point. It won't take that long to get there either, right? So basically then that means the natural log of x over x should be bigger than 1 over x after a certain point. Doesn't matter when it happens, just you have to know that it is going to happen. Yeah, it's going to happen at x equals e. Okay, so let's check 1 over x. We really don't have to. We should know that this diverges.
What test would we have to?
You can say it's known to diverge. That's equal to the limit as b approaches infinity. And this is equal to the limit as b approaches infinity of natural log of x from 1 to b. This is equal to the limit as b approaches infinity of the natural log of b minus the natural log of 1, which does not exist. Remember, this is true because the natural log of b approaches infinity. So we've shown that the natural log of x over x is always bigger than 1 over x. And the limit as x approaches infinity of integral from 1 to infinity 1 over x dx diverges. Therefore, 1 to infinity of natural log of x over x dx diverges. Let's take a look at that side note. Totally unnecessary, but you know, we're doing math here. 1 to infinity of natural log of x over x dx. That's equal to, well, let's take a look at the antiderivative first. Antiderivative of natural log x over x dx. Remember, down that list, eventually we'll get, or I think the third item in our list is u substitution, right? Let's try u equals natural log of x. du equals 1 over x dx. 1 over x is this right here. dx is this right here. So this is equal to the antiderivative of u du, which is 1/2 u squared du. No, plus constant. This means the limit as b approaches infinity 1 to b natural log of x over x dx is equal to the limit as b approaches infinity 1/2 natural log of x squared from 1 to b. I think you can see that this diverges. So as we were saying, that the limit comparison test isn't really necessary for this one, since you can integrate this directly. Okay. Enough of the side note. Let's look at 20. we have 1 to infinity e to the negative t over the square root of t dt. I'm making some adjustments to this. Give me 1 second. Okay. This one kind of looks like it's going to converge, or like it's going to diverge, because the denominator here is a root t. But if you think about that, really, that is kind of like 1 to infinity of 1 over e to the t root t dt. This is definitely bigger than 1 over t, right? Or this denominator grows faster than this, right? This denominator grows faster than t. So this is definitely going to, our suspicion is this is going to converge. This grows faster than t to the first power. So we think it's going to converge. Anything that grows faster than first degree is suspected to converge. Anything that grows slower than or equal to the first power is suspected to diverge. Yeah. Anything that is, any denominator that grows faster than a first degree, so t to the first power, x to the first power, anything that grows faster than that in the denominator is suspected to converge. Doesn't matter what it converges to. Just that integral is going to have a definite area. Okay. So take your pick. How can we, do we need to make the denominator bigger or smaller?
The denominator should be smaller.
The denominator should be smaller, right? Wait. Smaller would give me...
Diverges. If the denominator diverges, that means that 1 over it converges.
I'm getting a little bit confused here. We need to make the denominator smaller, right?
So that it's bigger.
So that's bigger. Okay. How can we make this denominator smaller? Well, I'll tell you what I would do. Remember, the trick is to make a denominator smaller, but also, or to make the denominator smaller, but have a function that's still going to converge. Right? That's really the trick here. So let's see, I have e to the t times the square root of t, right? Can't I just get rid of that square root of t? Wouldn't 1 over e to the t, wouldn't that be bigger than 1 over e to the t root t? I mean, these are both numbers greater than 1, right? And if I don't multiply one of them, I should get something smaller, therefore bigger.
So you can just get rid of either one of them. It doesn't matter.
Yeah. Yeah, just get rid of one of the factors will make it bigger, provided that that factor is greater than 1. Okay, so the limit, so we want to integrate this from, it's 1 to infinity, right? That's kind of hard to work with in the denominator. So I'm going to move it back to the numerator. Exponential functions are always easier to do in the numerator than the denominator. That integral is pretty easy. That's just negative e to the negative t. Okay, and substitute. Minus negative e to the negative 1 power. Let's take a really good look at what we have here. This is the limit as b approaches infinity of negative 1 over e to the b plus 1 over e. This totally goes to 0. And so we get that this converges. Okay, and since 1 over, since e to the negative t is bigger than e to the negative t over square root of t, if the bigger function converges, then the smaller function also converges. Hmm?
Why did you choose to eliminate the rat or the rat seed and not the...
Yeah, that's a really good point. If I got rid of the e to the t, I'd be stuck with 1 over square root of t. Square root of t grows slower than t to the first power. So that would give me a diverging integral, which would be counterproductive.
So you eliminate the one that's going to be greater than 1. You're going to eliminate the term that's greater than 1?
Well, depending on what I need to do. If I need to show, or if I suspect that the original function is going to converge, then I want to make sure that I have a converging function. Okay. 21. Each cross-section of an infinite horn bound by the x-axis and above by y equals e to the x is cut by a plane perpendicular to the x-axis. What? Is a circular disc with a diameter reaching from the x-axis to the curve y equals e to the x. That's really hard to read. Sorry about that. Anyone have an idea about what that graph looks like? That's good. Crickets. Let's kind of graph this then.
Was this in your next chapter?
Mm-hmm. Ooh, I think I erased too much there. the basis of this is the integral, an infinite integral. So what do we have? We have e to the x looks like this. Starts really close to the x-axis, and then whoop, shoots up. That's y equals e to the x. And we would just want to go from negative infinity to the square root of 2. No, not the square root of 2, the natural log of 2. Natural log of 2. And our cross sections are circles. Like that. It's kind of hard to see. This is the disk method, right? So the area here is going to be pi r squared. And we're going to have to start from negative infinity to the natural log of 2 of pi times the radius squared dx. So I guess the big trick is, what is the radius? E to the x over 2 would get half the distance here.
Yeah, it's the
Oh, it's the
diameter.
diameter. Oh, thank you. So I have all this wrong. So basically it looks like this. That ain't no horn. I guess it's kind of like a horn. So the radius is half of e to the x. That makes my formula limit as a approaches negative infinity from a to natural log of 2 pi times 1/4 e to the 2x dx. Let's take that pi over 4 and multiply it out at the very end. Okay. What's the antiderivative of e to the 2x? 1/2 e to the 2x. Very good. That's pi over 4. Limit as a approaches infinity of 1/2 e to the 2x. We're going from a to the natural log of 2. This doesn't look promising, right? Because I see an exponential function. I told you exponential functions grow like crazy. But the thing to remember is a is approaching negative infinity. Not just any infinity, negative infinity. So we're getting negative numbers here, right? Okay, so this is equal to, I'm going to take that 1/2 and stick it on the outside. So pi over 8. Okay. E to the natural log of 2 minus the limit as a approaches negative infinity of e to the 2a. So since
How come there isn't a 2 from that natural log of
2,
It's 2x and you put in natural log of 2. How come it's not 2?
you're right, that should be 2 natural log 2. You are correct. All right, we have a goes to negative infinity, right? 2a will also go to negative infinity. And what does that mean about e to the 2a?
0.
Yeah, this is going to approach 0. The exponent approaches negative infinity. So that's 1 over a very large number. So we get a 0 there. And let's try to make this look nicer. This is e to the natural log of 2 squared. Which is 2 squared. So we get pi halves. What is it? It's pi over 4, right? The constant. E to the 2x dx. Therefore, the volume is equal to pi halves. Okay. You try this last one, or do you want to? You only have 5 minutes. I'm not 100% confident we can finish it in 5 minutes.
Can you do it at the review?
I was hoping not to do it at the review. Do you want to do it now and stick around if you need to? Or do you want to stop and just get it on video?
Stop and get it on video.
I knew Tyler would say that.
Yeah.
What do you guys think?
You
Yeah.
can do it with the other class anyways.
I'm gonna try to do this with the other class. Do you want to stop or go? Okay, I guess you want to stop.
I didn't say anything because you know what I'm gonna say.
Yeah, you already said it. All right, there we go.